Welcome and thank you for joining this webinar from Orbit to Everywhere, Comprehensive Assessment of Modern Space Communication, prepared by Alpert Research Team. The choice of orbit determines everything about the network. The physics of distance dictates the economics, the latency, and the entire network architecture. Let's break down the three primary orbits, starting way out at 35,786 kilometers with GEO.
Geostationary Earth orbit, or GEO, is the veteran. It's located at 35,786 kilometers above the equator, and its key characteristic is that its orbital period precisely matches the Earth's rotation. That means the satellite appears stationary from a fixed point on the ground.
And that stationary quality offers massive operational simplicity.
A single GEO satellite can provide coverage to roughly 1/3 of the Earth's surface. Ground antennas are simple fixed dishes that don't need complex tracking. The drawback, however, is the significant distance. It imposes a fundamental speed of light penalty. The sheer distance results in very high latency, a round-trip delay typically ranging from 500 to 700 milliseconds.
That makes GEO inherently unsuitable for real-time interactive applications. Why does a delay of half a second matter so much?
For any application relying on continuous back-and-forth communication voice calls, VPN access, competitive gaming, or high-speed financial trading, that delay is just unacceptable. And while GEO capacity has grown enormously modern, high-throughput satellites can now exceed 500 GBPs using advanced multi-beam architectures, it really remains best suited for fixed data distribution and broadcasting, where latency is less critical than reliability and wide reach.
Moving inward from GEO, we find MEO.
Medium Earth orbit, or MEO, spans a wide altitude range, generally from 7,000 to 25,000 kilometers. MEO constellations, like those used by O3b, offer a balance. They provide better coverage per satellite than LEO, and they offer significantly lower latency than GEO, around 100 to 150 milliseconds, but they still require tracking antennas. MEO is the orbit of choice for all major global navigation satellite systems, or GNSS. We're talking GPS, GLONASS, Galileo. The altitude provides a good balance between orbital stability, coverage area, and the ability for those very weak signals to reach Earth effectively.
And finally, LEO, the low-altitude champion.
Low Earth orbit, or LEO, is defined by its proximity to Earth, ranging from 500 to 2,000 kilometers. This proximity is the single most important factor. Since the propagation distance is minimal, LEO achieves very low latency, typically between 20 and 50 milliseconds. That makes it genuinely competitive with high-speed terrestrial fiber networks for real-time applications.
But the physics of a low orbit means you have incredible velocity.
Yes. LEO satellites complete an orbit in a mere 90 to 120 minutes. This speed means an individual satellite is only visible to a user for a very short window, usually 5 to 15 minutes. This geometry demands large mega constellations, thousands of satellites organized across multiple orbital planes to ensure continuous, always-on global coverage, even in polar regions.
So if the satellites are moving that quickly, how does the network ensure a continuous session for a user? That sounds like a complex handover management problem.
It is, and handover is solved through sophisticated network topology and the user equipment itself. The network has to constantly calculate the ephemeris, the precise position of every single satellite, determining which one is about to set and which is about to rise. And the user terminal, like that ESA we discussed, must execute a seamless, instantaneous switch of its beam, often multiple times an hour, to maintain data session continuity.
The transformation is just undeniable.
It really is. What's so fascinating is just how quickly all these pieces have come together to take satellite from being this niche, high-latency tool into a core, competitive part of the global wireless backbone. This overview from the Alpert Research Team should really give you that full, integrated picture.
Modern satellite communication has evolved from a specialized broadcast tool into a core pillar of global connectivity, enabling broadband, IoT navigation, and resilient communication infrastructures. With the rise of LEO constellations, AI-optimized networks, and 3GPP standardized NTN systems, satellite communications are poised to serve billions of users and devices worldwide. This Alpert Research Team overview delivers an integrated view of the technologies, architecture, applications, challenges, and opportunities shaping the next decade of satellite-enabled connectivity. Interested in gaining a deeper understanding of the transformative power of wireless technology? Join the Alpert Research Team's webinars to explore cutting-edge wireless innovations, their applications, and their implications. Click the links below to learn more.